Okay, this is your Chapter 15 video supplement. Of course, this chapter is non-renewable energies, so it talks about fossil fuels and nuclear fission, both of which are non-renewable energy sources. Something that's not really covered much in the chapter are hydrocarbons, so I want to talk to you about what hydrocarbons are. And basically, if you look at the word, you can guess that they're composed of hydrogen, which of course is H from our element symbols, and C for carbon. So that's all they're composed of for the most part. And the simplest of hydrocarbons is a carbon with 4 hydrogens attached to it. Carbon's classic for taking on 4 bonds. That's why it's a great structural element. It forms the backbone of biomolecules. And of course, fossil fuels are just biological materials that were buried underground millions of years ago before they would completely decay all the way. So what's left is the fossil fuel that we harness for energy. So this is called methane. If you heat your house with natural gas, this is the majority of what's being used in that case. Hydrocarbons can come in all different shapes and sizes. And the difference between stuff like jet fuel and gasoline and stuff like that is the numbers and types of these hydrocarbons. Okay, so you can have a chain of different carbons with all hydrogens hanging off of them like this, and you can just make them larger and larger. In each case, carbon's going to have 4 bonds. Hydrogen 1. That's propane if you grill with gas. If you have butane, that's going to be in your lighter. These are all different hydrocarbons. Okay, octane, of course, you all know octane. So the question then becomes, what makes this a fuel? Where do we get the energy from? So when we talk about chemical reactions, we've done this already. It's going to write a chemical reaction here. It's methane, CH4, and we just wrote, plus 2O2, and that's because it's going to need to be balanced, yields CO2 plus 2H2O. This is a basic combustion reaction now. And of course, we're going to need something to get that going. That's the heat that you provide with your car or spark to light a fire, whatever. The key to a fuel is that once you get it going, right, it doesn't need any additional spark to keep it going. The fuel provides itself, self-sustaining. So I will tell you, and shouldn't be a surprise to you, that it takes energy to break bonds. It takes energy to break anything, right? It takes energy to break bonds. So as you can tell by looking at these, remember my analogy of Lego blocks, you can realize that all of these hydrogens here that are attached to these carbons are going to have to be broken off so that we can actually form CO2 over here. And you get the idea that these Lego pieces all have to be pulled apart and then they're reassembled over here. That's where the balancing comes from. Now, it takes energy to break those bonds, so you need to get that reaction started. But once it gets going, it turns out that energy is released when bonds are formed. So effectively, here's the water molecule. We have to form these bonds. That's going to release energy. That's H2O. Turns out that there's more energy released from forming the bonds than was needed to break them. That's what makes it a fuel. That's what keeps it self-sustaining. So this table here I'm going to allow you to fill out when you get the time. But what I'm going to do is fill out the bottom of it for you. So basically what we're looking at here is advantages and disadvantages and the reserves of petroleum, natural gas, and coal. I'm going to allow you to fill out the advantages and disadvantages because your chapter is structured in just that way that you can fill that out. But just to give you an idea for the reserves, and these numbers are subject to debate depending on who's reporting them, but just gives you a rough idea. Something around 50 years here. I'm going to put a question mark because now that we have newer technologies, we can go back in and get some of the oil we left behind in our old wells, and so this might go on a little bit longer. Gas we have a little bit more of, 90 years. I'm going to put 2 question marks there because if you looked at my slides, I had a link to a fracking video. Hydraulic fracking now is allowing us to get more and more natural gas, and you can actually use that for petroleum also. So that's why some of these numbers might be a little bit longer. Coal, 150 years with 1 question mark there. So we have more coal reserves. You could fill out the rest of that yourself. The next thing I want to take you through is radioactivity. And I think I defined for you excuse me, in my slides what radioactivity is, and that's the spontaneous disintegration of a nucleus. So something you might have thought about is the structure of the atom is such that we have protons and neutrons in the nucleus, right? And electrons on the outside. Now, protons are positively charged, neutrons are neutral, electrons are negatively charged. So, packed within that nucleus, electrons are kind of free with a lot more space. Packed within that nucleus is a bunch of positive charges. And you might have learned the law of charges, which says opposites attract, like charges repel. So why isn't the nucleus just flying apart as those protons, those positive charges, try to repel each other? In fact, that's what they do. The neutrons somehow hold that nucleus together, but sometimes, quite frankly, it's just unsuccessful. So it depends on the combinations of numbers of protons and neutrons whether it's able to be stabilized. So certain isotopes of certain elements are radioactive, and I defined isotopes for you in my slides. Atoms of the same element with differing number of neutrons. So I'm going to draw for you here 3 isotopes of hydrogen. These are the 3 isotopes of hydrogen. I'll explain to you this notation. The top number here is simply, start with the bottom number. The bottom number here is simply the number of protons. And protons we always call P+. That's a P for protons. The top number is the number of protons plus neutrons. Neutrons are just N with no charge. Electrons are going to be E with a negative. We don't need to worry about the electrons here, just wanted to make sure I showed you that. So if you subtract the bottom number from the top number, you get the neutrons, so you obviously wind up 0 neutrons here, 1 here, and 2 here. These are 3 naturally occurring isotopes of hydrogen. Turns out this one is radioactive naturally. Radioactivity has been around ever since the universe has been formed. Certain isotopes of certain elements are radioactive. So basically, you're radioactive. The computer you're looking at is radioactive. The food you eat is radioactive. It's not something humans created. But that is what we call our natural background radiation. Now, when something goes through radioactive decay, basically it's trying to stabilize itself and gives off, if you will, a chunk of its nucleus. So this is carbon. So this is an isotope of carbon. And the bottom number is what signifies what the element is. That doesn't change. The number of protons is the number of element. The element is the number of protons. Carbon's always 6. 6 is always carbon. Number of neutrons can vary. That gives us isotopes. Number of electrons can also vary. That gives us ions. So it turns out if this goes through what we call alpha decay, that's the Greek symbol for alpha. That's what an alpha particle is. The top number is 4. The bottom number is 2. What's left over has to be balanced. So just do the math. 6 minus 2 is 4. Look at your periodic table. 4 atomic number is beryllium, so this must be beryllium. And the top number is going to be 10. That is a radioactive decay. That happens to be an alpha decay. You don't have to know the different types of radioactive decay. I'm just giving you an example. These have to be balanced just like your chemical reactions. These are nuclear reactions, but they have to be balanced because we can't have protons and neutrons just disappearing, right? So this is radioactive decay. And carbon-14 is radioactive, obviously, where carbon-12 is not radioactive, so it doesn't go through radioactive decay. So which elements are radioactive? Turns out when you look at your periodic table, there's some reasons I didn't mention because it's beyond you, numbers of protons and neutrons, but one thing I will tell you, once you get beyond this atomic number right here, all the isotopes of all the elements are radioactive. No exceptions. That means all of uranium's isotopes, it has more than one isotope, it has a couple isotopes, they're all radioactive. Where here we just saw sometimes they're radioactive, sometimes they're not. Okay? But I want you to realize that everything beyond 83, when you look at your periodic table, that means you're going to go like this, then you come down to here, all those, and finish this here. Those are all radioactive, all their isotopes. So nuclear fission is a little bit different than radioactivity. With nuclear fission, what we have is the nucleus is really unstable, and it turns out that it doesn't just give off a small chunk. What it does is it gives off a large splitting of the nucleus. So, for instance, this is uranium right here, and uranium will go through fission. And Here's uranium-236. This is one isotope of uranium. It does this. It splits into these chunks. You don't have to worry about this in terms of, being able to do this. I'm going to show you this. It's all going to be balanced if you were to add this all up. But you notice the difference now. This is large chunks being emitted as opposed to just a small little alpha particle. Plus, we actually get 3 neutrons released. If you add these all up, it will be balanced. You can see right down here, do this really quick. 57 and 35 is 92. This is the difference. This is what gives off so much energy. It's this huge splitting of the nucleus. And this is what, was realized back, in the 30s. And ultimately, you can read your history about the building of the atomic bomb and all that. But this is what the concern was. There's a lot of energy released with this reaction. And that is the basis of nuclear bombs. That is also the basis of fission energy that you read about in your textbook. Fusion, if you will, is the way the sun works. And with fusion, what you're doing here is you're combining 2 small nuclei to give you a larger one. And this is what the sun does. So this is what your stars do. And this is just one example of a fusion reaction. Whoops, that should be a 2. These are 2 small isotopes of hydrogen. Usually with small isotopes this happens, as opposed to large ones we just saw. And you actually have a neutron released here also. But this is fusion. This is one of the reactions that powers your stars, our sun. And this is, if you will, a huge source of energy if we can ever work this out. Right now it's not practical. We have, model reactors, and we have different countries working on this and doing the science and working all the engineering, because the temperatures you're talking about are hundreds of millions of degrees to be able to carry this out. But this is fusion, and this actually would solve pretty much all of our energy needs if we could work this out. So that really brings the video to a conclusion here. So after you do your reading and you look through the PowerPoint slides and you watch this video, what you should get out of this, of course you're going to participate in your discussions also, but what you're going to get out of this is you're going to have a feel for what net energy is. Okay, and I talked a little bit about that too, but your book does a good introduction on that. You're going to go through your fossil fuels in your book, something I didn't do because your book does a real good job there. Just learning, exactly what these are and what are some characteristics about them, what are some advantages and disadvantages. Then, of course, make sure you can distinguish between fission and fusion. Fission is what we use now to get nuclear energy, and in this country, nuclear energy in general is used for electricity. Very similar to the way fossil fuels generate electricity, generate steam and turn a turbine, and that was mentioned in my PowerPoint slides. And then, so basically, pull all that together into allow you to do your worksheet and do your quiz, and that's the end of the video.